So I guess we are ready to start, inshallah. In the last lecture, we've looked at the time response of a first order system and a second order system. We've covered the first order in full details, but the second order system we didn't finish. There were a few slides that we didn't finish yet. So for a second order system, if I have the standard form of the second order system, G, where G is this, K over S squared plus 2 zeta omega n S plus omega n squared. And I have an input, which is U, and an output Y. I'd like to see what is the form of Y, what is the shape of the response of Y given U. So Y over U equals to this in the standard form. This is the standard second order system. And then if my U, the input, is 1 over S, if it is a unit step input, then my Y is as such. And depending on the value of zeta and omega n, I may have different responses. So my response could be something like this red line here. Or it could be something like this here, the blue line now. Or it could be something like this, the green line. So something like with a constant amplitude, sinusoidal with a constant amplitude. Depending on the value of zeta and omega n. The steady state value of this, if it is stable, y at t equals infinity, will be equals to what? Anyone? Without solving, we can use one of the theorems of Laplace transform to get the value of y at infinity at steady state. So what will it be using the limit? Anyone? المحروقي أو السادي حمد? One of you? What will be y at infinity given this transfer function? السادي?
0.
What will it be? You can use one of the theorems of the Laplace transform. We call it the final value theorem. So y at infinity will be equal to, in that case, the limit of what? As s tends to 0.
SYS.
SYS. True. So what will it be? In that case, if you substitute here with s, if you multiply this by s and let s equal 0.
YS. K over S squared.
K over omega n squared, true. K over omega n squared. So that will be the steady state value, which is this one, this value here. So this one will be K over omega n squared. Now the red line, when will I have this response, the red line? In which case? Let me first of all get the poles. The poles will be S12 equals, but before that, I think someone wants to be admitted. Basil. Okay, so let me go back to here. So the poles will be, if I'm to get the pole of this one, what will make this 0? The poles will be what? Will be minus 2 zeta omega n plus or minus 4 zeta squared omega n squared. It's just a quadratic equation that I'm trying to solve. Minus 4 omega n squared. The whole thing over 2. Then I can simplify it a bit by removing this 2 and this 2 and then taking here 4 omega n squared as a common factor. So it will be minus zeta omega n plus or minus omega n, the square root of zeta squared minus 1. Now, when the solution will have this red plot, when I have what? To get this red line here. When you have real pools or complex pools?
Real pools.
Real pools.
Real.
When I have real pools, what will happen? I'll have R1 over S plus P1 plus R2 over S plus P2 plus, because of the input, because of 1 over S, I'll have R3 over S. So what will be the solution? The solution will be R1 e to the minus P1t plus R2 e to the minus P2t plus R3. So that will be the solution. And this R3 will be omega k over omega n squared in that case, this R3. So when will this have real solution? When zeta equals 2?
0.
When zeta equals
1.
When zeta equals 0, it will not, because I'll have then a complex number. So when zeta equals 1. So zeta equals 1, what will happen? This will be 0, and I'll have 2 real pools. So the 2 real pools will have the same position, because this part is 0, the whole thing. But there is another case, when zeta is larger than 1 or less than 1.
Larger than 1.
Yeah, so when zeta larger than 1,
less than 1 to have a
yeah, so when zeta larger than 1, what will happen? This will be positive. Or not? When zeta larger than 1, this will be positive. This one here will be positive, and therefore I will have 2 real pools. So 2 real pools will give me this response, will give me this red line. What about the green line? The one with which is oscillation, which has oscillation with constant amplitude, this green line.
When zeta equal to 0.
When zeta equal to 0. So when zeta equal to 0, what will happen? This will be 0. So S12 will be 0. And then here, this is what you call 0. So it will be plus or minus j omega n. It will be just a complex number. I mean, imaginary part. The real part of the complex number will be 0. So someone wants to be admitted. Hamza. So we'll have different what you call responses depending on the value of zeta and omega. If we have that blue line, the blue line, let me draw it again here. If we have the blue line, so I'll just draw it again here separately. This one. This is T, this is Y, and I'll have something like this. And this is the steady state value. We can somehow put some design specification that we'll use later to design controllers or to describe the behavior of the system. One of them is the time to the first pick. This one, time to the first pick, to the first what you call maximum. So that's TP, time to the first pick. Another one is time to settle to the final value, to omega, to k over omega n squared, which is this one. So if the value of my output y reaches a certain what you call band and stays within that band, it doesn't get out of it. It gets into this band and then stays within the band. This we call it the settling time. And another design specification could be the rise time also, TR, rise time. And then we have also the percentage overshoot. Percentage overshoot is this value here, the maximum, C maximum minus C final. This what you call magnitude here, or this value, divided by C maximum minus C final divided by C final, and then multiply this by 100 to get the percentage. This we call it percentage overshoot. So these what you call specifications, I can use them to describe the behavior of the system. Rise time and time to the first pick will give me a measure بيعطيني يوم ما نقول كذا وصف لسرعة الاستجابة، سرعة استجابة السيستم. Time to the rise, I mean the rise time and the time to the phase pick. The settling time will give me also some sort of a measure of the speed of response, but it's more to do with the speed of settling down to the final value, the settling time. And then the percentage overshoot, which is this one, will give me a measure of the stability one, and also a measure of the oscillation, how much oscillation do I have in the system. So that's what we have covered last time. So let's go to the what you call the presentation now. So we have these measures: time to the phase pick, settling time, and percentage overshoot and rise time. We can relate them to the pole position. We can relate to the pole positions or to zeta and omega n. So we can relate them to zeta and omega n. So this is the pole position, as we said. You have the real part, which is zeta omega n, and you have the imaginary part, which is this. Now, if we draw it on the S-plane, this is the real part, zeta omega n, this length here. This is the real part. And then we have the, what you call the imaginary part is this length, the blue one, this one. This is omega n, the square root of 1 minus zeta squared. Now, if I try to get the magnitude, this length here, I will have this squared plus this squared. And if you do that, you'll find out that it is equals to omega n. Let's try it. We'll try it here in the one node. If we go here and try to do that. So what I have the real part is zeta omega n. And the imaginary part is omega n square root of 1 minus zeta squared. And I want to know what is this length. This length here, let's call it A. So A, let's just put it as A squared. A squared is what? Pythagoras?
Zeta omega square whole square.
So zeta squared omega n squared plus
omega n squared
1 minus zeta squared. And what will that be? Can you simplify it?
Omega square
Equals to?
Omega square.
Omega squared, because this one will cancel out of this and I will get omega n squared. So A equals to omega n. So the length, this one will be equals to omega n. This angle here, theta, is related to zeta because cosine theta equals what? Sorry, this is omega n. A is omega n, not omega n squared. A squared is omega n squared. So what is cosine theta?
Zeta omega n.
Zeta omega n over omega n, which is zeta. So zeta is related to this angle here. Now the settling time, Ts, equals to 4 over zeta omega n. And zeta omega n is what? Is the real part. So it is 4 over the real part, zeta. So this is settling time. It means if I have my what you call pole here, where the real part is zeta omega n, then any pole along this line, any pole here, will have the same settling time or not? Same settling time, because the settling time is 4 over the real part. And if the real part is the same, then no matter where you are along this line, you'll have the same settling time. Time to the phase pick, Tp, equals to pi over omega n 1 minus zeta squared, equals to pi over the imaginary part. If this is the imaginary part, this one, then it is pi over the imaginary part. So if you have poles with the same imaginary part, no matter what is the real part, then they will have the same time to the phase pick. So any pole along this line, the green line, any pole here, no matter what is the real part, if the imaginary part is the same, if this one is omega d, then the time to the phase peak will be the same, regardless of what is the real part of your what you call pole. So regardless of the real part, you will have the same time to the phase peak. And for zeta, if you are along this line, let's put it in red. If you are along this line, okay, zeta here is the same because theta is the same, so zeta is the same. And if zeta is the same, then your percentage overshoot will be the same because percentage overshoot is related to zeta. So we are trying now to relate the pole position to the response of the system. So this is the pole position. Now the time to the phase peak is pi over the imaginary part. So no matter where you are, you'll have the same. I mean, if the imaginary part is the same, your time to the phase peak will be the same. Settling time, again, if you have the same real part, then your settling time will be the same. Percentage overshoot, if you have zeta or theta, in that case, the angle, this angle here, if it is fixed and you are somewhere here, then your percentage overshoot will be the same. It will not change. So TP is inversely proportional to the imaginary part of the pole, while TS, which is the settling time, it is inversely proportional to the real part of the pole. Percentage overshoot is constant along radial lines of the same theta. So the percentage overshoot here is the same, here it is the same, here it is the same, no matter where you are along that line. Just to repeat again, if the real part is fixed, then your settling time is fixed. If this real part is fixed, then your settling time, the time to here, will be fixed. You may have different percentage overshoot. You may have different time to the phase peak. These are time to the phase peak, which are different, but your settling time, TS, will be the same if your real part is fixed. And the same for the time to the phase peak. If your imaginary part is fixed, then your what you call time to the phase peak, you can see here this one is the same as this one, even though the percentage overshoot settling time is different. But the time to the phase peak is the same because the imaginary part is the same. And the same for the percentage overshoot. The percentage overshoot, this length, will be the same if you are along this line. If you are along this line, percentage overshoot will be the same. It will not change. Now, let's do a small exercise. Let's say I have this position of the pole. S12 equals to minus 3 plus or minus 7j. So the imaginary part is 7. What will be my time to the phase peak in that case? Let me remind you of the formula for the time to the phase peak. Just try to write it down. This is the time to the phase peak. Pi over the imaginary part. And this is the settling time, 4 over the real part. And the percentage overshoot, if you can write this down, exponential of minus zeta times pi over the square root of 1 minus zeta squared. So I think you have written that down. Percentage overshoot, exponential minus zeta pi over 1 minus zeta squared. So now let's go to the our problem here. What is the time to the phase peak?
Pi over 7.
Pi over 7, because the imaginary part is 7. What about the settling time?
4 over minus 3.
Over 3 because it's time, so it will not be negative. 4 over 3. And then the percentage overshoot. Percentage overshoot, maybe the calculation will take time, but we know how to calculate it from that formula. So the to get zeta first, I need to get zeta. So zeta, you can get it by knowing the angle between that line and the between this line, joining the pole to the origin. So this is my theta. So theta will be tan inverse 7 over 3, which is 66.8. So now what is zeta? Cosine of 66.8. So if we do that, we get zeta, which is 0.39. Okay, so we know zeta. We can now calculate percentage overshoot. Time, as we did before, pi over 7. And the percentage overshoot, we use this formula. We just substitute with zeta equals 0.39, and you get the percentage overshoot using that formula. So this is how you will calculate the percentage overshoot. Settling time is easy, 4 over 3. Let's say we have this system, okay? And then I have this graph showing the response of the system. This graph here, showing the response of the system. This value here is 0.02. And then the rise time is 1.8 over omega n. And the time to the first peak is this one here. We can use settling time instead of this. Settling time, I think around 5. This is the settling time. And TS is 4 over zeta omega n. Okay, let's go back to the system. This is the system that we have. So how can I get M, B, and K if I have the response due to the unit step input? F is 1 over S. And I have this X. This is my X, X of T. Can I get those values, M and B and K? What should I do first? I want to get K, B, and M. I need to get the transfer function or not? So what will be the transfer function, anyone?
5m s squared
5m
x
s squared x plus
b s x
plus
kx
kx equals to 2f. So it means x over f equals to what?
Two over
2 over
5m
5m squared, m squared plus
bsx.
bs plus k. So I need to compare now this one with the what you call the the standard second order system. The standard second order system. The standard second order system is that x over f equals to k over s squared plus 2 zeta omega ns plus omega n squared. I need to compare it with this, and then from the graph I can get zeta and omega n. If I know zeta and omega n, I can get m and b and k. But now this one have 5m here, and this one have 1 here. So I need to simplify this. So how can I write it in a different way? X over f, I can write it as, I can take 5m as a common factor. So it will be 2 over 5m. Then I'll be left with s squared plus what?
B 5 over 5m
B over 5m s plus
plus K over 5m.
over 5m. So I can have it that way. Now I will just remove this and put it beneath 2 there. So this will be x over f equals to 2 over 5m. Just another way of writing it. And then in the denominator, I'll have s squared plus b over 5m S plus K over 5M. So now what is omega n squared?
K over 5M.
Over 5M. And 2 zeta omega n equals to?
B over 5M.
B over 5M. So now I'll go to the next slide here. So we have that what you call K over 5M equals omega n squared, and B over 5M equals to 2 zeta omega n. And I have this graph. How can I use this graph now to get B and K and M? I need to get omega n and zeta, but I need something more. But let's start with omega n and zeta. How can I get it? We have this one. This is equals to 5. So this is one equation. And this is equal to, if you see it here, I cannot see it clearly, but it is 1 point. This is 1, and this is 2. So this is here nearly 1.8. So it means time to the first pick is 1.8. So now I have two equations with two unknowns, zeta and omega n. So I need to solve these two to get omega n and zeta. So I need to solve these to get it. So I can use, let's say from here, I can take that zeta equals 4 over 5 omega n, and then substitute here and solve for omega n. So anyway, if I know omega n and I know zeta, but from these two equations, I can get omega n and zeta. Then I will get from here and here, I will get K over 5M and B over 5M. But still, I don't know what is M, what is B, what is K. So I need one more information. From where can I get it? My equation is that X over F, if you remember, it is 2 over 5M divided by S squared plus B over 5M S plus K over 5M. So can I get something more to know what is K and B and M? I know that at steady state, my X is 0.02 when F is 1 over S. So can that help me?
Take limit.
Yeah, so take the limit of S, X of S as S tends to 0. And that will be from here. F, remember F is 1 over S. So it will be the limit of S as S tend to 0 of 1 over S, which is F, times 2 over 5M divided by whatever I have here, divided by this. So this will give me what? If I do the calculation, S will go with S. So it will be 2 over 5M divided by what?
K over 5M.
K over 5M. K over 5M. So 5M will cancel out with 5M. Oh, sorry, with 5M. And I will end up with 2 over K equals 2.02. So from here I can get K. From this equation, I can get K. K will be, very quickly, I think you can know it. This is 0.02, and this is 2. So K equals it should be easy. 2 over K is 0.02. So K equals
2 over 0.02.
So it is
100.
100. So K equals 100. I know K, and I know K over 5M, so I can get M. And I know B over 5M, I can get B. So I'll be able to know all the other parameters this way. I'll be able to know K, which we calculated to be 100. And from these two equations for TS equals 5 and TP equals 1.8, I can get zeta and omega n. And I know that K over 5m is omega n squared, and B over 5m is 2 zeta omega n. And I know K, I can get B and M. From here I can get M, and from here I can get B after knowing K. So we can use the response to know the parameters very easily, and we call that identification of the parameters. Okay, so
Doctor,
that was
why we say TS is 5 here and 1.8 divided by omega n? Why we choose 1.8?
Why we chose 1.8 from the graph? Because this is the graph. I'll remove this, discard, and then go back to the graph here. From this graph here, we are given this graph. So this graph says if I calculate my time to the first peak, time to this peak here, this time, it is because this is 1, this is 2, and nearly this period here is 1.8. 1.8. Settling time is the time needed for my output to get closer to the steady state value. And just roughly, I calculated it to be 5. So at this time, it will reach 2% of the final value. This is the definition of the settling time. So from the definition of settling time, I didn't use this one in the problem. It was given that time to the rise time is 1.8. I could have used that, but I've used the settling time since we defined settling time to be 4 over zeta omega n. We were speaking about settling time and time to the first peak and percentage overshoot. Does that answer your question?
Yes, doctor. Thank you.
So, yeah. So this is what was remaining from the previous lecture. There were about 5 slides that I didn't explain last time. So I explained them now. Now we'll get into today's topic. But before that, we are supposed to have quiz 1 this week, but we didn't have it, quiz 1. So we'll move it to week 8. Week 7, we'll have the midterm. I mean, the next week is week 6. So the week after, week 7, on the 3rd of March, we'll have our midterm. During next week, during the lecture, where I will take 30 minutes from each lecture to give you some tutorial so that you will have some practice problems to prepare yourself for the, plus the homework that you had before to prepare yourself for the midterm. But the first quiz, instead of having it in week 5, because it was not possible because of the online, we'll have it in week 8. It will be. You also, for the lab, you got an email from Engineer Nasaiba. So please reply and fill the table that he sent, the Excel file, because if you don't, then you'll miss the lab and then you'll miss 10% of your grade. Because we'll not repeat the lab. It will be next week and the week after. So you need to do it as soon as possible, because she told me that some of you didn't sort of fill the table. So you need to give her your names as a group, so that, and choose the time so that you can start doing the experiments. Any questions regarding the quiz, midterm, and lab? We'll discuss more the midterm next week during the tutorial. Any questions?
We need to take something to the lab, doctor.
No, you don't have to take anything. Just a notebook and maybe a pen and calculator.
Okay.
So that if you get some data, or if you want to write something, you have a place where to write it. And the time, you have to agree with her on the time. We looked at your free slots, and then she suggested some times. So you can choose the slot that suits you. But please do it by today, because if you are, because she has also to arrange to tell you if this is okay. Because if you choose a time where everyone is choosing that time, then it will be difficult for her to handle a large group. So she may tell you, no, this time is not possible. Choose another time. Okay, so we'll continue with today's lecture then. Today we'll look at the block diagram. Block diagram is when you sort of take the Laplace transform in order to take the transfer function of a complicated system. You may have different blocks representing different parts of the system. So for this system here, we may have a block representing the dynamic of the antenna, and maybe you will have another block representing the what you call the gear here, that you have the gear train and the motor, and another to sort of describe the behavior of another part of the system. So you may have a block like this one here, which is made up of a number of transfer functions. So you have GS for this, GS for this, GS for this, just GS for that. And you may need to simplify this in order to simplify this so that you can get only one block that relates the angular input here to the angular output there. So theta to theta desired. You may need only one GS equivalent to do it. So how to do that? This is the topic of today's lecture. How to do this simplification. Before starting with trying to do the simplification, let's see what are the different things that you will have in the diagram. You can notice here that we have a block. We have a summing junction, a summing point where you are summing signals. And you have also some sort of a special sort of arrangement where you have this feedback. You are feeding back the signal to the same block. So those are some of the things that are basic in any block diagram that we may need to look at and to see how the signal is handled in such situations. So the first one will be, let me just skip this. The first one is the block. A block is just a transfer function that relates the output to the input. So C equals to R times G. Another one is the summing junction, where you are summing signals. So here we have R1 plus R2 minus R3. So C, the output, is R1 plus R2 minus R3. So this is a summing junction. Another what you call thing that you may notice in a block diagram is a place where you have the same signal going to different places. So it's R going here and there and here. So we call that a pick-off point in the language of what you call a block diagram. Now, we may have blocks put in cascaded form where you have one block after the other. So this signal will be multiplied by G1 to get X2. G1 times R is X2. And then the same signal is multiplied. So X2 is multiplied by G2 to get X1. So this is X1 multiplied by G2, which is this, to get X1. And then the same signal is multiplied by G3. So this one is C equals to X1, this one, which is RS times G1 times G2. This is X1 times G3 to get C. So if I want to get the overall C is equal to R times G1. So R times G1 times G2 times G2 times G3. So if I take R as a common factor, I'll have G1 times G2 times G3 times R. So the equivalent GE that gives me C given R is what? What is the equivalent G? When I multiply it by R, I get C. Is what? In terms of G1, G2, G3. It is equals to G from here.
G1, G2, G3.
G1, G2, G3. So when you have cascaded blocks, to get the overall block, you just multiply them. You multiply G1 by G2 by G3. So this is the equivalent block. G1 times G2 times G3 will give me C given R. So when I have them in series, this is how I will combine them to get the overall equivalent transfer function. If I have them in parallel, if I add them up, so I have R times G1 plus R times G2 plus R times G3, I'm adding them up plus or minus, then the overall what you call transfer function will be the sum of these transfer functions, G1 plus or minus G2 plus or minus G3 will give me the equivalent what you call transfer function. So the equivalent transfer function is plus minus G1 plus minus G2 plus minus G3 if you have them in parallel as such, if you had them added up in this way. So this is the second arrangement. Now we may have that in this form, in the feedback form. So if I want to replace this with an overall transfer function that relate R to C, I need to know how to do it. So what I will do, I will take E first. What is E? Let me do it here, it will be easier in the note because it's easier to write here. So let's say I have this as G, and this is my output C, and then I'm feeding it back through another transfer function H. And then I have here plus O minus R, which will give me E. And I want now to get C over R to get the equivalent transfer function that relates C to R. So what is E? Let's start with E. E is what? R plus O minus, because we have either plus or minus, what? H times
C.
So CH, because I have this signal multiplied by this, so it will give me CH. And then I subtract it or add it to R. So this is E, and then C equals E times G. E times G. So it is equals to R plus or minus CH, this is E, times G. But remember, I want to get C over R. So how can I do it?
Divide by G.
Divided by G, yeah? Or should I take this as a common factor and get C as outside? So I'll have C, instead of plus minus, because I'm going to move it here, it will be minus plus CHG, or not, equals to RG. I think that's right, or not?
Yes.
Now I want C over R, so let me take C as a common factor. So it will be 1 minus plus HG equals to RG, which means C over R equals what?
G
over
1 minus plus HG.
So this will be my equivalent transfer function. This will be my equivalent transfer function that will replace this. Okay, so if this is minus, it will be here plus. Okay, and if it is plus, it will be here minus between 1 and HG. So that will be my overall transfer function in case I have a feedback loop. So here it goes through the same exercise. You have C equals G times E, and then E equals to R minus H times C, and so on. The same exercise that we did. So you will get this as your overall transfer function. Okay. So for the feedback form, we'll get it this way. Depending on whether it is negative or plus, you will get here either plus or negative. It will be switched with the sign. And we call this here open loop transfer function in the language of, the control, if you have feedback. And we call the GE, the equivalent, as the closed loop transfer function. We'll be using these terminologies from time to time. So I will remind you again that this is the open loop transfer function and this is the closed loop transfer function. Now, sometimes you might need to simplify it. You may need to move summing junctions either here or to move it from here to here. sometimes. So how you can do it? Let's say for this one, if I move it, what should I do? If I move it such that I have my block here and my what you call summing point there, okay, and then I have my R there, and I have my X here, and then from here we'll get C. So for R, C is what? If I can write it here, what is C? C equals to what? R from this diagram. What is C?
Plus X.
Minus plus X times G, or not? It should be that way. Now, what about this C? If I put it this way, if I move now this summing junction from here to here, what will happen? What will be my C? C equals to, this C will be what? RG, because R is multiplied by G. But for X, if I put it this way, now X will be just added without being multiplied by G. So what should I do to have this X multiplied by G? So that I have the same effect. I will have the same situation as here. I will have this way. I'll have it that way. So what should I do here in this line? I should multiply by
G.
G. So I should have here G also. If I make that movement, if I move the summing junction from here to here, I should multiply X by G and then add it, so that I'll have the same effect. I'll have this. So this is what will happen if you are to do this, to move it from that point here to that point. You need to multiply X by G in order to have it that way. So to move this summing junction to here, you don't have to remember this, but you just have to, I mean, you don't have to memorize it. But with time, you will know that you have to do this in order to get the same effect. And we'll do some exercises today. Now, what happens if you want to do the opposite? Now, if I want to go back from here and move it to there. So if I have it this way now, yeah, if I have the opposite, if I have my, so I have R here, and I have G here, and then I have C, the output. Now I want to move X from there to here. Here you can notice that X is not multiplied by G. C equals to RG minus plus X. So X is not multiplied by G. If I do it this way, now X will be multiplied by G, just like R. So I may need to do something here to multiply it by something else. What should I multiply it with? So that's
1 over G.
1 over G. So if I have here 1 over G, then I will have X multiplied by 1 over G and then multiplied by G, which means I'll get X without being multiplied by G. And that's what we'll do for that case. So for that case, we'll have it this way. To get the same effect, we'll just divide X by G and then multiply it again by G, so that I will have the same effect as the one that I have here. It will be not multiplied by anything because I will cancel out this by multiplying it by 1 over G. These ones are easy. It's not difficult. If you move this one here, what should you do? Because this is the only one multiplied by G, but this one is not multiplied by G, and this one is not multiplied by G. So if I put here G, what should I do here and here?
Multiply it by 1 over G.
So multiply by 1 over G, and that's what will happen. We'll have 1 over G here, 1 over G there, to be able to move it that way. And the same if you do the opposite. If we move this one here, there, so I mean, if you move this one to there, then nothing will happen, I think. It should be okay. Yeah, nothing will happen. You just move it in that case, because it's already multiplied. So it should be fine in that case. Now let's take some examples. We'll start with this simple one. So how can we simplify it? Any suggestions?
Add G4 and G3.
Add or multiply? G3 and G4.
Multiply.
Multiply. So G3 and G4 will multiply them. What about G1 and G2? This is feedback. So it will be
Add them.
Plus.
and add them if it is this way. If I have a signal here, and then the same signal goes here, and then I'm adding them here. Then this one, G1 and G2, I will add them. But this one, I'm getting the output, I'm feeding it back. So I'm not adding.
Multiply.
So this one will be feedback. Feedback, just to remind you, for feedback, it will be something like this. Let me go back. It seems I skipped. Parallel. This is addition. This is feedback. So it is this one in the numerator divided by, if this is minus, this will be plus. 1 plus this times this. So it is this one in the numerator divided by 1 plus this times this. This one times this one. Okay? I think you can remember it. If we go back now to this one, our example. Yeah. How can I do it?
G1 over 1 plus G2 G1 times G1.
Yes. So we'll have it that way. So it will be G1 over 1 plus, because here minus, G1 times G2. So that will be a feedback. So now I have this situation. I have this one G3, G4, and I have this one here. So now I have them one after the other. So what will I do?
Multiply.
Because it's very similar to this. So I'll just multiply them. I will get this as my overall transfer function. So this is for the first example. Let's take another example, this one. This one is more involved, but it's not that difficult also. So G2, G3 is easy, or not? G2, G3, you just multiply them. And if you multiply them, you will get this. G2, G3. And then H1, H2, H3, you're adding them because it's the same signal. If you notice this signal and this signal and this signal, they are multiplied by this and then they are added here. So this is addition. And these two are multiplied by one another. So if I do that, I will end up with this. G2 times G3, and then these three are added. And because I put the minus here, this one, H1, will be minus. So plus here, minus. Because here it is plus and here it is minus, so it will be minus. I mean, plus, minus. And this one here, it is plus. And because I have here minus, I should have a minus there. And this one is plus, and here minus. So I will have it as plus because the minus is already there. Okay, I think it's fine. Now, these two are what? This one and this one. Feedback. So for feedback, I can have it this way. So these two will be as the feedback. And then you have one here and one there. You multiply them by one another. And this will be the overall transfer function. I think it's okay. Or should I go through it step by step?
It's okay.
Fine. So we'll go to another example. This one here now. Here we'll do it slowly. So the ones that you recognize very quickly, let me know which one that you can we can do very quickly.
G1 and G2.
Yeah, G1 and G2 multiplication, and you'll get this. What else?
H1 and H2.
G3, G4.
G3 and G4. Yes, these two I can add them because you have addition here. So these ones I can do it. So let's do that, those two. So if I do this one and do this one, I will end up with G1 times G2 and G3 plus G4. What else?
Feedback, Doctor. H1.
So we have feedback here.
have
This one.
three feedback.
H1 و H2.
H1 with G1 times G2. So this is feedback. So this will mean this will be G1, G2 over 1 plus G1, G2 times H1. It will give me this. So that's, we can do it also. But there is, so this we did it. But there is another thing here, actually. If I do some trick, I can also do something else here, because here this one is also, is it feedback here? But I have this problem here. I have this line coming out. So I need to move this point from here to cancel it and to move it to here, to bring it here. But I have a small problem. This signal is multiplied by G5. But this one, the one that I canceled, is not multiplied by G5. So what should I do to make it possible?
Divide by G5.
Divide. So I will divide here by G5, 1 over G5. So that this signal is also not multiplied by G5, just like this one. This one is not multiplied by G5. So if I multiply by G5, I divide by G5. Then I will get that one. So that's what we have here, this one. So these two, I moved that one. I moved that line to there. Now you'll notice that these two, I can easily multiply them by one another. And then if I do that, I will have a feedback here. Okay. And if I do that, then I have this times this in series. And if I do that, then this times this in series, and this one is a feedback. So this will be the procedure now. So this one is done. Okay. Now these two are multiplied. These two multiplied to get this. Okay. And now this one is a feedback, which is this one here. Okay. And now these two are multiplied by one another. So these two, this one and this one, you multiply, you get this. Now this 2 is feedback. It looks complicated, but the process is the same. You have one what you call G here. This is G equivalent. And you have another one here, H, let's call it. So this GE and H is the feedback. So you'll just you have this one in the denominator divided by 1 plus HGE. So it will be GE over 1 plus GEH. But H is not simple. It has a ratio of 2 transfer function. And this one is not simple. GE is a bit complicated. And then if you simplify it, you'll get this one. If you simplify your what you call expression, you'll get that as your final GE. I think the process is okay. Clear. Maher, is it okay? Rashid?
Yes, Doctor. Clear.
So I think it's clear. Let's now do a simple example here. If you notice, يعني كل الأمثلة هذه اللي سويناها نعتبرنا أن هذه G1 و G2 و G3 بدون ما نكتبها ك let's say K over S squared plus 1 or something of that sort. We just put it as G1. But G1 could be this. Okay. So let's take now an example. It is simple, but now let's say G1 is 1 over GS squared and G2 is K1 plus K2S. And let's simplify it and then see what we can do with the simplification. What will be next? What will be next is to design or analyze the system. So here we have 2 in series, this one and this one in series. Okay. So you will, if you will multiply them by one another. So what will happen? This one will be this way. And here we can say this is 1 minus plus. Now, this one here, GE, what? GE is what? Equals to multiplication. So 1 over GS squared times K1 plus K2S. So that will be my GE. Now, if you have a feedback for this one, what will happen? What will be your overall GE? Equals to what? In terms of GE. Write it in terms of GE. It will be GE divided by
1
plus GE times 1. So it will be that way. So if this is my GE. So if I do that, G will be equals to GE, which is K1 plus K2S divided by GS squared. Divided by GS squared. All of this divided by 1 plus the same thing, K1 plus K2S divided by GS squared. Now I will, instead of 1 here, I can write it again as GS squared divided by GS squared. So this is 1, which means this GS squared will go with this GS squared, will go with this GS squared. So I'll end up with K1 plus K2S over GS squared plus K1 plus K2S. And this is what we have here. So this is my overall transfer function. Now I might be interested in analyzing, because after you simplify, so I can simplification of this or simplification of this. Once you simplify, you want to do some analysis or design. So let's say that I reach this stage now. I have this one. I want to do some analysis. Maybe I want to know what is J, what is K1, what is K2 from the response of the system. So I will do the analysis now after simplification. Okay. So let's take another example. This one here, let's say. And the closed loop transfer function will be given as such. If you do the simplification as we did just now. فأعتقد الخطوة هذه من هنا لهنا خلاص عارفينها كيف نسويها ولا؟ For this simple one, because this is my GE now. I think you can do it, huh?
Yes, Doctor.
Yes. So let's say that I have now this as my overall transfer function. So my poles are given as such. Okay, this is my pole. Okay, and now I may do some analysis. I might be interested in knowing what happens when A equals 4K or 2K. When A squared equals 4K, what will happen? And when A squared is larger than 4K, what will happen? And so on. I may do some analysis. تحليل لتأثير ال A وال K. I may do that here. So if this one here, A squared or 4K minus A squared is if 4K plus A squared is larger than 0, what will happen? What will you have? Will you have real numbers or complex numbers in that case?
Real number.
Real numbers. If this is positive, if this is positive, if this is positive, then you'll have real roots or real poles, which means it will be overdamped, we call it. It will be overdamped. You'll have what you call a solution or a response, which is like this, overdamped. There is no oscillations.
Doctor, we can do it by calculation, right? To find the roots.
Yeah, you can do it by calculation if you know what is A and what is K, yes. But let's say now I want just to study, I want to analyze. I did my simplification. يعني القصد إن الحين أنت عملت simplification وبعدين what you will do. وش بتسوي بهذا simplification؟ تبى تسوي analysis أو تبى تسوي design. فخلنا نقول الحين عملنا هذا simplification لهذا simple system اللي هو هذا عملنا simplification. الحين نعمل design أو نعمل analysis. Just to illustrate to you, يعني just to show you what you will do next after doing this block diagram reduction or block diagram simplification. You will do some analysis like what we are doing now. Okay, so if this is positive, it means you'll have real roots. Real roots, it means your simulation or your solution or your response will be something like this, which we call it overdamped. If it is equals, I mean, if this is equal to 0, then you have two real roots, which are the same. Then if this is 0, then you'll have two real roots, which are the same, which means your response will be similar still to this one, very similar, but your two poles will be the same. Underdamped, if this is now negative. If this is negative, you'll have a complex number. If you have complex number, it means your system will have some oscillations. So your response will be something like this, and we call this underdamped. So it's not fully damped, it's not overdamped, and it's not critically damped, it is underdamped. And undamped, if you don't have real part, then it will be undamped, which means you'll have oscillation which are undamped. You'll have a solution which have oscillations with the same amplitude. So your solution will be something like this, undamped. There is no damping in the system. Energy is not damped. Energy will remain in the system forever. Okay. So this is just to do some analysis. Maybe another analysis could be, let's say we have this system and we want to choose now K. We want to do some design now. Choose K such that the percentage overshoot is 10%. So again, I will simplify my block diagram to get my overall transfer function or closed loop transfer function, which is this. Now, what is my omega n squared? Equals what? Omega n squared. If you compare this to the standard second order system. Any suggestions? Omega n squared equals?
K.
K. So omega n squared is K. What about 2 zeta omega n? Five. Yeah, so 5. So we know omega n squared is K and 2 zeta omega n is 5, which means I'm told now choose K to make the percentage overshoot 10%. So the percentage overshoot is a function of what? Percentage overshoot. Let me remind you again, TP equals pi over the imaginary part. The settling time equals 4 over the real part, zeta omega n. Percentage overshoot equals a function of zeta, equals to exponential minus zeta pi divided by the square root of 1 minus zeta squared. So a percentage of 10%, I can get zeta from it. So if the percentage overshoot is 10%, 0.1 will be equals to the exponential of minus zeta pi over the square root of 1 minus zeta squared, which means ln 0.1 will be equals to minus zeta pi over the square root of 1 minus zeta squared. So from here I can get zeta. Okay. Now I want to choose K to get this zeta. So I have that omega n squared is K and 2 zeta omega n is 5. So how can I relate zeta to K? Again, and 2 zeta omega n equals 5. So how can I get zeta as a function of K? What should I do?
Put omega n.
So put omega
Square
n.
root 5.
So it will be 2 zeta. Omega n will be what? Square root of K.
K.
آسف الكتابة هنا على ال PowerPoint presentation is not that easy. Sometimes it does some very strange things. So this will be the square root of K equals 5, which means from here that zeta equals what? 5 over 2 square root of K. So if I know zeta, by knowing that I have a percentage overshoot of 0.1, I can get K from this equation. And if I know K, then I can design this system to have this percentage overshoot. القصد الحين ما احنا قاعدين نصمم او نحلل، الحين بس باغي اقول لكم ان البلوك diagram reduction or simplification is good for us because later on we can do some analysis or we can do some design once we simplify our block diagram. هذا هو القصد. فهذه الخطوات بتعرفوها مع الوقت، مش فيها اشكاليه وفي امثله كثيره في الكتاب بالاضافه الى بعطيكم امثله اخرى الاسبوع القادم. لكن الفكره اللي باغي اوصلها انك انت الحين عملت بلوك دايجرام ريدكشن، عملت سمبليفيكيشن، وبعدين هل هي مساله مجرد سمبليفيكيشن؟ لا، عملت سمبليفيكيشن على اساس تعمل اناليسيس، عملت سمبليفيكيشن على اساس تعمل ديزاين، عملت سمبليفيكيشن على اساس اقدر اعمل simulation later on when we go to what you call to sim this one, this MATLAB or C lab, I may do simplification to be able to design my controller, and also to be able to sort of do simulation in the simplest possible way. So now I can just take my block here, take, let's say, a transfer function, put it here, and now I know what is my transfer function. I will just put it there. And I know my input sources is a step input. And I have sinks, which is something that will allow me to do some simulation or to see my results. If I can simplify it such that it is only one block, it will be better, instead of having a complicated system here for me. So if I simplify it this way, it's better for me, or not? I think it's better. It makes things easier that way. فهذا القصد من simplification. انك تعمل simplification على اساس انك تقدر تعمل simulation، لانه بيكون معك simple system made up of one block. السهل ايضا من ناحيه انك تقدر تعمل design، تقدر تعمل analysis as we are doing now for very simple systems. فواضحه الفكره بيكون. فقبل ما نواصل بنحط امثله ثانيه، لكن قبل ما نواصل باخذ. let's go back now to the presentation. Any question so far? The full solution is there, so you can go through it again just to convince yourself. But as I told you, the basic idea is that we need to simplify block diagrams, and then we can do something with it. And this is one of the things that you can do with the simplified block diagram. So I'll move on. Another example here. Let's simplify this block diagram, and I think this will be the last one. We have another one there, but you can go through the rest yourself. So we'll just do this one. Any suggestions how to do it? What do we have here?
A feedback.
Feedback.
Here is a feedback. And then here, I'll just try to simplify it a bit by saying we have here a block, a transfer function, which is 1. So what about these two?
Another feedback.
Is it feedback, or is it, if you notice the difference between feedback is that the output is fed back. Here, the output is not fed back. You have input and you have input, and then you add them up. So this is in parallel. So you add them up. So these two, you add them up. And then once you do that, you have this and that in series, or not?
Yes.
So multiply them, yeah. And then now we have one big block here. So we have this big block here, this one. And then we have another block here. So this is what?
Feedback.
But we have a small problem, but it's not a problem. I can have that feedback, and then you can see this signal. It's the same signal going here also. But that's not a problem. I can have this as feedback, these two. I can have this as feedback and have here a big sort of block there. Okay. And now I have this and this big block in series. So I can multiply them by one another, and I will have this situation after doing this. And now I have feedback with this being 1. And then I can do feedback. So those are the steps that you will do. So that's what happened here. We have this 3. And then you have a feedback of this one. And then you have G1 and this, you multiply them, and then you take a feedback. So you'll get this as the overall transfer function. So the exercise, I don't think it's that difficult. It's just a matter of recognizing where you have a feedback, where you have blocks in series, and where you have them in parallel. Let's do another one. What about this one here? Just to know the difference between parallel and feedback. So what is the suggestion here? we have this two situation. This one, let's call it A, and this one, let's call it B. So A is what? Yeah,
Feedback.
so this is feedback. What about B? Parallel, because I'm adding them up. This signal goes here, and the same signal goes here, and then I add them. So this is parallel. Now I have A, and I have B, and I have C. They are in series. I'll multiply them by one another. So now you have this in series. So you know here you have S minus 2, S minus 2, and then you have here this one divided by 1 plus this times this, and this is what we got there. And now you multiply them out because they are in series, and then you have feedback. So very similar to the previous example. So I think I will end it here. We have another example here that you can try later at home. Should we do it? Maybe this one is different. Let's do it. This one is different a bit here. It has a small trick here, so let's do it together. Will be better. We have feedback, not feedback. We have two in. Is it feedback or أحسن أسألكم كيف تخبروني؟ هذه feedback هنا ولا this is addition؟ feedback. لكن المشكلة الحين إذا سويت هذه وحطيتها كفيدباك بتضيع السيجنال هذا اللي طالع منه، لأني أنا بحط هذه كبلوك والسيجنال هذه طالع من داخل البلوك فبتضيع. فهيش بسوي على أساس إني
أطلعها برا.
أطلعها برا. فأطلعها برا. إذا بحتاج إني أطلع هذه السيجنال من هنا أطلعها وأحطها هنا. لكن هذه السيجنال مضروبة في G1 ولا؟ لأن جاية هنا مضروبة في G1، فإذا جبتها هنا المفترض ما تكون مضروبة. فإيش أسوي؟ لأن هي طالعة مني ما مضروبة في G1 وأنا بجيبها الحين هنا.
1 over G1.
So I put here 1 over G1. So 1 over G1. And then I can have it from here. So that's what we'll get. We'll have it from here, but I'll divide it by G1. الحين المسألة سهلة. هذه feedback وهذه وش يسمى كأنهم in parallel. Add them up. And then بيكون معي هذه البلوك اللي هي هذه feedback وهذه البلوك اللي هي addition G2 plus 1 over G1 G2 plus 1 over G1 ومضروبة في الG3 مضروبة في الG3 فمضروبة هذه اللي هي ذي وهذه اللي هي الاديشن وهذه اللي هي الG3 من الأول موجودة ضربتهم في بعض طلع لي overall transfer function. So I think you got the idea, the basic idea how to do it. For any examples, I'll give you more examples. There is some more examples here that you can try about 1 or 2. But also I'll give you more examples from, I'll suggest more examples from the book. And then I think this should be easy to handle by everyone, inshallah.